Another critical consideration is emotional and social awareness. For such intelligence to operate in human environments, it must be able to detect and respond to emotional cues. This includes understanding when a person is stressed, confused, or frustrated and then adjusting its behavior to match the emotional context. Systems capable of effective computing and behavioral modeling can analyze voice tone, facial expressions, and body language to infer emotional states. For example, a system acting as a personal assistant might choose to delay non-urgent matters if it detects that its user is overwhelmed or under pressure. This kind of sensitivity is essential if the system is to be trusted and integrated into daily life. Despite its potential benefits, this intelligence also brings with it a number of risks and consequences. One of the most pressing concerns is alignment, ensuring that the goals and behaviors of the system match human values and priorities. If the system becomes too independent, there is the danger that it might pursue objectives that do not align with human well-being. Even well-intentioned actions could lead to unintended harm if not properly guided by ethical boundaries. The possibility of losing control over such a system is not purely theoretical and is frequently discussed in research and policy circles. Another consequence involves the future of work. This intelligence has the ability to automate a wide range of jobs, not only in manufacturing or transportation but in areas that require decision-making, analysis, and creativity. Roles in education, healthcare, law, design, and even scientific discovery may be affected. While this could lead to increases in productivity and innovation, it could also result in significant economic disruptions, changes in labor markets, and increased social inequality if not carefully managed. Moreover, the independence of such systems means they can set and pursue their own goals. While this might lead to incredible breakthroughs, it also requires strict oversight. Systems that generate their own objectives might not always value safety, privacy, or fairness unless these priorities are built deeply into their framework. This creates the need for strong ethical guidelines, continuous monitoring, and systems of accountability that can respond to unforeseen outcomes. Artificial general intelligence represents a significant step forward in technological development. Its ability to learn, adapt, and act independently holds tremendous promise in research, education, healthcare, and many other fields. However, this same potential creates serious challenges in terms of understanding, control, and social impact. As the field progresses, the focus must remain not only on what such systems can do, but on how they should act in relation to the humans they serve. The key to success lies not only in engineering power, but in ensuring that power remains aligned with human dignity, safety, and the complex values that define our shared world. Automated speech recognition is the process by which spoken language is converted into written text through the use of digital systems. This technology allows machines to interpret human speech by analyzing and processing sound waves, ultimately transforming audio information into a readable format. The process begins with the capture of sound, which in its original form consists of continuous, naturally occurring vibrations in the air known as analog waves. These analog sound waves are the result of varying pressure caused by a sound source, such as a human voice, and are perceived by the human ear as speech. To be usable by a computer, these analog waves must be translated into a digital format. This is done by capturing the sound through a device that converts the fluctuations in air pressure into an electrical signal. The electrical version still mirrors the original wave's shape and flow but must go through another conversion step to become digital data. This process is carried out using converters that sample the wave at regular intervals, measuring the strength of the signal at each point in time. The outcome is a stream of numbers that represent the original sound, now in a form that machines can process. Once the speech has been digitized, the next step involves feature extraction. This process reduces the raw, complex waveform into a more manageable and meaningful set of values. These features are essential for identifying the content of the speech, and the process also helps filter out unnecessary noise or variability. In its raw state, a digitized audio signal fluctuates unpredictably and contains little immediately useful structure. Feature extraction methods transform the signal from a time-based representation into a frequency-based one, allowing the system to recognize pitch, tone, rhythm, and articulation with far greater clarity. A particularly common method for feature extraction in speech recognition is the use of mel-frequency cepstral coefficients. This technique attempts to replicate how the human ear responds to different sounds. It focuses on frequency ranges that humans naturally hear more clearly. To apply this method, the audio is divided into overlapping time slices, each lasting a few dozen milliseconds. Each slice undergoes a mathematical transformation that reveals the audio's frequency content. Filters tuned to the human hearing scale are then applied, emphasizing the most relevant parts of the sound. The resulting values are further simplified through a transformation that reduces them to a small set of coefficients. These coefficients capture the general shape of the sound spectrum and serve as a compact summary of its characteristics. After the features have been extracted, the system proceeds to segmentation. This step breaks the continuous stream of sound into smaller, linguistically meaningful pieces such as phonemes, syllables, or full words. Once segmented, the information is compared to known language patterns using advanced recognition methods. These include systems trained on vast collections of spoken language examples.